Okay, hello everyone. I'm Dragana Grbic, computer science PhD student and Ken Kennedy Fellow this year. And I'm going to talk about measuring, analyzing application performance at Exascale that I've been working with my advisor, John Malakrami. So what are my research group interested at? So we're interested in measuring the performance application that we execute at Exascale systems at DO laboratories. So we measure the performance of executions performed at Frontier, Aurora. We use the HPC toolkit performance tool to collect the performance of large-scale executions. So on this image here, you can see a trace view of a large execution of lamps on Frontier, 64K ampere ranks using 64K GPU tiles. We collect a large data, and then we're interested, okay, we have this huge data, and how can we analyze and inspect and detect the problems in our program in a fast and responsive way. So for this example, we performed this execution and we collected 4 terabytes of data. On this image, I'm just showing the GPU traces, but the entire database contains 4 terabytes. And we can see, if you look at this trace view, there's like strange communication delays and patterns of repeated idleness. And okay, so we have a huge data, we look at this and say, okay, why we have this strange anomalies, and how can we analyze and detect the anomalies in our program. So what we're interested, we have a huge amount of data. We want to automate the analysis or process of large-scale data. If we're dealing with large-scale executions, the first thing that we did, we developed a new framework in Python. So we don't want to analyze the data with a graphical user interface. We want to provide a more automated and programmatic interface. And we're interested in developing strategies for exploring a large data and finding the regions that are most important for us to detect the performance. So we have strategies for automatically pruning code regions with low information content. If you have a calling context tree with millions of nodes, we want to feed that in our model and extract the most time-consuming regions. And once we have that, for the example on the previous slide, we had an execution 64K ampere ranks. And we can say, okay, we're interested, we want to see the load balance across my ampere ranks. I don't want to look entire 64K ampere ranks. I want to estimate my results on smaller subsets. So we enable sampling performance profiles from large-scale executions and estimate load balance using profile subsets. So above you can see, like, I was calculating the load balance for the most time-consuming regions by extracting smaller number of ranks. And here on this graph, I was plotting the load balance. So on the previous slide, we had a trace view that we saw the idleness and network delays. And here I managed to detect these anomalies by plotting the communication time by only looking at a smaller number of ranks. So we can identify problems in seconds from terabytes of measurement data. And the last thing I want to mention is the work I did at Lawrence Livermore last summer. We also support combining the data from multiple executions. So we have application that we want to analyze the performance, but we're interested, okay, how is my performance of my application being affected if I compile my application with different compilers, if I execute on different platforms, if I run on different scales, and if I run with different input arguments. So on this image on the right, if we have like 3 experiments, 3 calling context tree, I worked on a tool that takes those 3 calling context tree and creates one union tree, which we can use to analyze the performance across multiple experiments. If you have 3 experiments, we have a union tree over there that has values for each experiment, and we can see, okay, if I execute my application on one platform, this was my performance. If I execute on a different platform, this was my performance. And this is the short description of my work. If you want to hear more, you can come to my poster reception. That's it.
All right.